converting between magnitude direction vectors and xy vectors. It should work in all programming languages. Okay, so today we're going to be changing a rectangular vector made up of x and y into a polar vector made up of direction and magnitude and vice versa. So how do we do it? Part 1. Rectangular to polar vector. So here we have our rectangular vector graph, and we'll add the variables for magnitude and direction. No, we're programmers, not mathematicians. Much better. So, let's focus on the magnitude first. This graph is actually a secret right angle triangle, so all we need to do is find the hypotenuse of it, which we can do by using the formula a squared plus b squared equals c squared. So now, as you can see, when we add the numbers to our formula, we have found the magnitude. Practice time! The vector is meant to follow the mouse, but it's currently not doing that. So, let's program the magnitude to function properly. I made a function that takes a position variable as input and is intended to return the magnitude of the position as output. We can use our formula for this. So, let's return the square root of our x position squared plus our y position squared, and we can square them by multiplying them by themselves. You can use a power function to square the numbers, but I think it just makes it more complicated and messy. Sensational. Okay, so now let's find the angle. We can use the formula angle equals arctan y on x, where the x and y are the x component and y component of the vector. Arctan is also called atan and inverse tan in some places, and you'll find it in most calculators and programming languages. If you have the magnitude of the vector like we calculated previously, and an x or a y component of the vector, you can use the other trigonometric functions to find the angle of the vector. Specifically, you can use the inverse trigonometric functions, like arccos or arcsine, depending on which component of the vector you want to use as a reference. You can use the x and the magnitude using arccos, or you can use the y and the magnitude using arcsine. And as mentioned before, you can use the x and y using arctan. But it's important to adjust the angle correctly based on the signs of the x and y, since it will affect the quadrant in which the angle lies, because then it won't work, as you can see over here. To adjust the angle correctly for arctan, you need to look at the signs of the components as follows. If x and y are both positive, it's in the first quadrant, which is 0 to 90 degrees, and in this case, we can just do nothing. If x is positive and y is negative, it's in the fourth quadrant, and we can also do nothing in this quadrant, but it's showing negative 33 degrees, which it can also be 227 degrees. If you want, you can add 360 degrees to change it to 227 degrees. As you can see here, they both work the same way, but one of them is 0 to 360, and another one is from 0 to 180, and then minus 180 to 0. If x is negative and y is positive, it means that you are from 180 to 90 degrees, and it means that you're in the second quadrant. If you're in the second quadrant, you have to add 180 degrees, and now, as you can see, it lines up with the mouse. Fixed, not fixed, fixed, not fixed, fixed. If x and y are both negative, it means you're in the third quadrant. If you want it to be from 0 to 180 and minus 180 to 0, like you can see on the left, you have to subtract 180. But if you want it from 0 to 360, you add 180. When x is exactly 0, it likes to flip. So if x is 0 and y is positive, we need to make sure the angle is 90. And if x is 0 and y is negative, we need to make sure it's negative 90 or 270 degrees. Note that your angle will be in radians. So if you want the angle in degrees, you'll need to convert it by multiplying it by 180 divided by pi, or like 57.295899598. Sometimes it can be a function, and sometimes it can also be a variable which you can multiply with. The difference between inverse and normal trigonometric functions is the input and output of the functions. Normal trigonometric functions take an angle as input and output the ratio of the sides, while the reverse trigonometric functions take the ratio of the sides as input and output the angle. Just saying that in the code, I am using radians and I'll write them in degrees at the side. Okay, so I've made a nice little table with everything we need to cover, and let's start with our cos. So here we just have a completely normal acos function. I got the adjacent and divided by the hypotenuse because that's how you use it, and let's see what happens. So as you can see, it malfunctions when y is less than 0. Now let's see how we can correct arc cos. So here we have the same thing, but if the y position is less than 0, we subtract the angle from 360 degrees. So it's like we're going at 360 degrees and then going backwards from the angle. As you can see, it works perfectly fine. Next, we have arcsine. So this is just a plain normal arcsine function. It's used how it's intended, and that's it. And as you can see, it's quite broken. Let's see how we can correct arcsine. This is basically the same, but if the x position of the mouse is less than 0, we go from 180 and then we minus the angle, which gives us the correct angle. Now finally, the most important thing, we have arctan. Listen up! We have atan, so this is just used as intended, as normal, opposite on adjacent. And as you can see, it's quite broken and stuff, so this is how you correct arctan badly. So this is the first thing I tried to come up with to fix it, and if the x position of the mouse is less than 0, we just add 180 degrees, and at first it looks like it's working, but there's quite a bit of issues and it's a bit broken and stuff. This is how you correct it correctly. So we start by setting the angle to the normal atan function, and then we're going to check if it's in the second and third quadrant, aka the mouse position's x position is less than 0. Then we're going to narrow it down even more and check if it's in the second quadrant, which means if the y position of the mouse is more than 0. And if it is, then we add 180 degrees to the angle so that we flip it and, get the correct angle. Else, so if it's below 0, which means it's in the third quadrant, we're going to subtract 180 degrees. And this is because we're doing the 180 degree atan function, not the 360 degrees one, but I'll get to that later. Now, if x is exactly 0, it means that it's probably gonna glitch out like how the atan function does. And if the y position of the mouse is above, the angle has to be 90 degrees, and if it's below, it has to be minus 90 degrees or 270, but that's in the other one. This is a separate way to correct it correctly. Now for the 360 degree one, it's quite similar. We check if the x position of the mouse is less than 0, but this time we don't narrow down and we just add 180 no matter what quadrant it is, if it's second or if it's third, doesn't matter. And in this one, if it's in the fourth quadrant, we also have to add 360 degrees or it will be like minus, and we don't want that. And the rest is the same, apart from instead of it being minus 90 degrees, it's 270 degrees. I know this is the best way. Look at it, it's so simple. It's just one function. It takes the y position and the x position as input. And all it is one function. Look, it works out of the box perfectly. Well, it does have like the minus 180 and the minus 90 stuff, but you can just fix it with this. And if the y position is less than 0, it just adds 360. Boom, fixed. Amazing. So how do we do it? Part 2. Polar to rectangular vector. So here we have our polar vector graph, and let's start by finding x. So as I said before, we have to use the inverse trigonometrics to find the angle, and we're going to use the not inverse to find the sides. So to find the y, we need to use cosine, since it uses adjacent, which is also sort of y, so we're going to have to find the adjacent. So we'll write down the formula of cosine, and now we're going to replace it with our own variables of x and magnitude and rotation, and then we're going to substitute them with the actual numbers. And we're going to remove the 7.07 from one side, and then we're going to add it on the other and multiply it so that we can get x on its own. So here we have our formula, and if you would like to write it in code, this would be the code. So we just return the magnitude multiplied by the cosine of the direction. Okay, so now let's do the y. So for y, all we need to do is use sine instead of cosine and just repeat the process. And all I changed was I wrote y instead of x and sine instead of cosine. And here's our formula, and if you want it in code, here you go. You just return the magnitude multiplied by the sine of the direction. Practice time. So this is basically the same, but the function is in radians and the direction variable is in degrees, which means we need to change the direction variable into radians so that the function can use it correctly. And this is the same thing, but instead of cosine, it's sine. Instead of x, it's y. Thanks for watching the video. I spent lots of time on it, and I'd really appreciate if you could donate so I can make even bigger and better videos. As you can see, I spend lots of time and money on my videos, and it would be a great help if you guys donated some money to help me. It's been a bit difficult to balance school and stuff, so it would be helpful. So thank you.